Hello everyone, and welcome to today's presentation on computer systems. I'm excited to have you here as we explore some fundamental concepts in GCSE computer science. Today, we'll be focusing on logic gates, which are the building blocks of digital circuits. Over the course of this presentation, we'll cover what logic gates are, how they work, and why they're so important in computer systems. So, let's get started and dive into the fascinating world of logic gates. Today, we'll explore how to interpret truth tables for logic gates and logic circuits. Understanding these tables is essential because they show us how different input combinations affect the output of a gate. We'll focus on some common logic gates, AND, OR, NOT, and XOR, and see how each one functions. Recognizing these gates helps us decode the behavior of basic digital circuits. We'll also discuss the role of Boolean logic in computer systems. Boolean logic provides the foundation for all digital decision-making, enabling computers to perform complex operations through simple true or false values. By the end of this slide, you'll see how these concepts connect to the bigger picture of digital electronics and computing. This knowledge is crucial because it helps us understand how computers process information at the most fundamental level. Let's take a closer look at Boolean logic, which is fundamental to how computers make decisions. At the heart of any computer is the CPU, or central processing unit. This is essentially the brain of the computer. The CPU fetches instructions from main memory and then executes them to perform tasks. Now, within the CPU, there's a critical component called the ALU, or arithmetic logic unit. This is where all the logical decision-making happens. When the CPU needs to decide, for example, whether a condition is true or false, it relies on the ALU to make that call. And this process of making decisions based on logical conditions is what we call Boolean logic. So, in short, Boolean logic is the foundation that allows computers to evaluate conditions and make choices, enabling all the complex operations we rely on every day. Boolean logic is represented using logic gate symbols. Logic gates use Boolean logic to take one or more binary inputs and produce a single binary output. When we talk about logic gates, we're referring to the basic building blocks of digital circuits. These gates interpret the inputs, which are usually zeros and ones, and then apply a specific logical function. The result is a single output that depends on the type of gate and the inputs it receives. Understanding these gates is essential because they form the foundation of all digital devices. By mastering how they work, you can better grasp how complex electronic systems process information. So, in essence, logic gates visually symbolize how Boolean logic is implemented in digital hardware. They are the practical tools that turn logical concepts into real-world electronic signals. All right, let's talk about the AND gate. As you can see, both inputs need to be true, or in digital terms, both need to be 1 for the output to be true as well. If either input is false or 0, then the output remains false. This is clearly shown in the truth table where only when A and B are both 1, the output Q is 1. This concept is fundamental because it demonstrates how logical AND operations work in digital circuits. The key point here is that the output depends on both inputs being true. In the context of our overall theme, understanding AND gates helps us see how complex decision-making can be broken down into simple, reliable logic functions. So remember, for an AND gate, both inputs have to be true for the output to be true. Now let's take a closer look at this table. It shows different combinations of inputs A and B, and the resulting output Q. Notice that whenever at least one of the inputs is true, meaning either A or B or both, the output Q is true as well. For example, when A is 0 and B is 1, Q is 1. Similarly, when A is 1 and B is 0, Q is 1. And of course, when both A and B are 1, Q is still 1. The only time Q is 0 is when both inputs are 0. This behavior is characteristic of what we call an OR gate. The key point here is that only one of the inputs needs to be true for the output to be true. It's a simple but fundamental logic gate in digital circuits, and it aligns perfectly with our theme of understanding how basic logic operations work. This table helps us see clearly how the OR gate functions in practical terms. In this slide, we're looking at a simple example of how a NOT gate works. The table shows that for a given input, which is A in this case, the output is Q when A is 0, the output Q becomes 1, and when A is 1, the output Q switches to 0. Essentially, this demonstrates that the NOT gate reverses the input signal. It's important to highlight that a single input results in a single output, and the core function here is inversion. So, if we think about it in terms of logic, the NOT gate flips the value, turning true into false, or 1 into 0. This simple but fundamental concept is a building block for more complex digital circuits. It connects back to the overall theme of how basic logic gates form the foundation of digital computing. Understanding these simple inversions helps us grasp how more sophisticated logical operations are constructed. Now, let's take a closer look at this table to understand how the XOR gate works. As you can see, we have two inputs, labeled A and B, and an output Q. The key point here is that Q is true only when exactly one of the inputs is true. For example, when both A and B are 0, the output Q is 0. When A is 0 and B is 1, Q becomes 1. Similarly, if A is 1 and B is 0, the output is again 1. But when both A and B are 1, the output drops back to 0. This behavior means that the XOR gate produces a true output only when just one input is true, not both. It's a fundamental logic gate used in many digital circuits, especially in situations where we need to detect differences between two signals. Notice how the diagram highlights the importance of the fact that only one input can be true for the output to be true. That's the core concept of the XOR operation, and it's what makes it so useful in digital logic design. It's all about detecting exclusivity, whether one, and only one, condition is met. Now, let's take a closer look at how multiple logic gates can be combined to form a complete logic circuit. In this example, we see that the output from an OR gate is then fed into a NOT gate, which essentially reverses or inverts the signal. This combination allows us to create more complex logic functions by connecting simple gates together. The table illustrates the different input combinations and the resulting output, highlighting how the NOT gate modifies the OR gate's output. This demonstrates the power of building complex circuits from basic components, which is a fundamental concept in digital logic design. It also shows how understanding these simple building blocks helps us understand more sophisticated systems in digital electronics. Let's take a closer look at this table, which illustrates how different combinations of inputs A, B, C, D, and E affect the output Q. Each row represents a specific input set, and the corresponding value of Q shows whether the circuit outputs a 1 or a 0 for that combination. What's interesting here is to observe the patterns. Notice that Q is 1 in some cases and 0 in others, depending on the specific input conditions. This table helps us understand the logic behind the circuit's decision-making process. As we analyze the table, pay attention to the key input combinations that result in Q being 1. These are critical because they highlight the specific conditions under which the circuit activates or outputs a true signal. The overall theme here is about how complex logical relationships can be represented in a tabular form, making it easier to analyze and design digital circuits. This table is a foundational step toward understanding how logic gates and circuits work together to produce desired outputs based on multiple inputs. In the context of our presentation, this table underscores the importance of mapping out all possible input states to fully grasp the circuit's behavior. It's a practical way to visualize and verify the logic before implementing it physically.